Hello, am I audible?
Hello, Ishan. Yeah, you're audible. You can go ahead.
Okay, I'll start then. Okay, very good evening to all the participants. I hope my voice is clear. If anytime during the presentation, if my voice goes off or if there's any problem, otherwise do let us know. And before starting the session, another thing that I would like to tell the participants is that at the end of the session, we have planned like time where we can like discuss your queries. We can go over some questions and so on. So during the presentation, if you have any doubts, please make a note of them or drop them in the chat box. And from there, we can take it forward. And also, if another thing, I'll just say it right now only, if any thing gets missed out, like if any part or any query or anything is not discussed today, we'll go ahead with it in tomorrow's session. So I'll begin with my session then. So today's part, we'll be mainly focusing on epidemiology and biostatistics. So what I was told was that these two topics were to be the most important, especially for the upcoming competitive exams. So we'll focus on these today. The remaining topics will be covered in the next session, and also any doubts or anything which is not clear today from these two topics, we can discuss that as well. So I'll just briefly give you like a theoretical background on both these two topics, because now's the time when we need to focus more on like just getting the answers quickly rather than sitting down with the theory. So I'll get on. So just start with an introduction to epidemiology. Now, as such, the definition is not required, but what is required is the name of the person and the year. So John M. Last, and in the year 1988. In certain, like sometimes in the MCQs, there'll be like, there is a question that who gave the definition of epidemiology. So that's over here, John M. Last. And also another thing, like a quick point to remember is that there are three components to epidemiology. That's your disease frequency, the distribution of the disease, and determinants of the disease. So again, from the definition, the two keywords which you should pick up is distribution and determinants, so of the health related states and events. So the aim would be description, identification, and provision of the data. So I'm not getting into too much detail over here. We'll move on. So to fulfill these three aims, we have the three broad epidemiological designs, which include your descriptive studies, your analytical studies, and your experimental studies. So in a line, if I have to talk about each of them, so your descriptive studies will help you raise a question that if you feel, say, for example, a researcher might or any professional might think that is there a link between smoking and lung cancer, the classical example. So your descriptive study will just be able to help you frame a question on what is like how lung cancer and smoking, they are existing. Now your analytical studies that is where you get an association between the two. That is it positively impacting it? Is it negatively impacting it? And finally, using your experimental studies, you can you can prove the association and also your experimental epidemiology will tell you like what is effectiveness and efficacy of like a particular agent on another. So we'll be getting into the brief of all of these now. So before that, what we'll discuss are what are your basic tools of measurement in epidemiology. Now, it is also important to remember this because sometimes in MCQs, these questions are asked, like you might be asked a question on the rates, ratios, proportions, that you might be given options and then be asked that which of the following is not a rate or which of the following is not a proportion or vice versa, and so on. So how like you can identify these is that, so a rate is a measurement that will give you the occurrence of a particular event in a given time period. So an important part to remember in the rate is that the numerator is based on the denominator. For example, if we go with a death rate, so number of deaths in 1 year in 2000 divided by the mid-year population. So as you can see is that the numerator and the denominator, they are related to each other. Now, just there might be crude rates or specific rates. Now, again, this can be asked in a question that to distinguish between the two. So your crude rate will be a generalized rate, like your examples can be the birth rates, death rates, fertility rates, and so on. Like they're just looking at the rate. They're not looking like what is the reason behind that particular rate, which is what your specific rates are going to explore. So for example, here it's like an example that observed rates due to a specific disease, that what is the rate of the tuberculosis, like how many new cases of tuberculosis are being reported, and so on. And your standardized rates are rates which are obtained from any bodies. So we next move on to your ratio. So your ratio will just express the relation in size between two random quantities. Now, the important thing, what you need to understand in a ratio, like how you can differentiate a ratio, is that the numerator is not a part of the denominator. So here, if we use the sex ratio, for example, say, if we give a sex ratio of say 3:2, like if the male to female ratio. So for every 3 males, there are 2 females, or like the doctor population ratio, if that is 1:1000, that means that for the 1000 population, there'll be 1 doctor. And finally, we move on to our proportions. So your proportion will indicate the magnitude of that particular of the denominator of the numerator in comparison with the denominator. So the main difference between a ratio and a proportion is in a ratio, the numerator and the denominator are not related, but in a proportion, the numerator is always a part of the denominator, and it's expressed as a percentage. So for example, if you want to find out, say the given here is that what is the proportion of the dental caries in a particular population. So we'll take here they've taken a village as an example. So we'll see how many children have dental caries in that village at that particular time, divided by the total number of children that are present in the village at that time, and we'll obtain a percentage out of that. So next we come into our prevalence and incidence. Now, before the relationship, I'll just quickly tell you what they are. So your prevalence is the existing number of cases. Now, an important thing to remember over here is that your prevalence is not a rate, because prevalence is a proportion, because you're seeing that what is like how many people in a at a given point of time in a given population are affected by a condition. So if I go back to the previous slide, so this is basically giving you your prevalence of dental caries in that particular village, but your incidence, that is a rate. So your incidence is how many new cases are being added. So the relationship between incidence and prevalence is that prevalence is equal to the incidence into the mean duration. So as the example, it's given here in a simple way that say if we take something like, say we take oral cancer as an example, that per 1,000 population, there are 10 new oral cases of oral cancer per year. And if we see, so this will give us our incidence. So the incidence is 10 cases per 1,000 per year. And if we want to look at the prevalence over a period of time, say we consider a period of 5 years. So we multiply the incidence with the time period to get the prevalence rate. So we can say that the prevalence rate of oral cancer is 50 per 1,000 population when we take into consideration the mean duration. Now, one particular question which was asked in previous these competitive exams is that it was in relation to incidence and prevalence, that which of the following statements are true, that both are ratios, both are proportions, then incidence is a rate while prevalence is a proportion, and the fourth option was vice versa. So in a question like that, the answer would be that incidence is a rate, but prevalence is not. So this is an easy analogy again to remember incidence and prevalence. So your prevalence is already the cases that are existing, and the incidence is just the new cases that are added to that. So next we'll move on to the types of epidemiological studies. Like how previously I told that there are descriptive, analytical, and experimental designs. So before that, broadly, they can be classified as non-experimental and experimental studies. Now in your non-experimental studies, you'll get your descriptive and analytical studies, and the experimental one is, of course, there you'll have your randomized and non-randomized trials. So again, when we are doing population-based studies, again, that is mostly where your descriptive studies come into picture, where you're trying to form a question, where you're trying to generate your hypothesis. And when it is more of individual based, then we are looking at particular individuals or groups of interest within a larger population. So based on that, it can be classified as your cross-sectional studies, your case control studies, and your cohort studies. So this is a study which is conducted at one point of time. Your case control study is the one which looks at already events that have occurred. And your cohort study is where you'll follow the group of interest to see what the outcome is. So just briefly describing them one by one. So in your descriptive epidemiology, there are again 3 words that you need to remember, which is time, place, and person. So this could also be asked in a question that what are the factors of descriptive epidemiology. So your time would be that what is the relation of the disease with time? Is it increasing over time, decreasing over time? Then is there any particular time like of the year or any seasonal variation of any disease or condition or so on? So your place will be the area where it is, this could be like, it could be in a particular community, it could be in like a city, a district, a state, country, like a whole region, and so on. And your person is like among like that whole population, that which is the the person or the group which is of interest. So just giving you like a quick recap of what are the steps. So they include that you define the population to be studied, that who it could be, like your doist, the population could be school children. Then it could be medical professionals or any professionals from a particular field, or in any particular, like it could be also like something among IT employees and so on. Next would be defining the disease that is to be studied. So say if I take an example that we want to see that if there is any relation between backache and IT professionals. So defining the disease, we'll see that lower back pain or lower back issues and so on. Next would be describing the disease by the 3 factors: time, place, and person. Measurement, then comparing with the known indices, and then finally formulation of the hypothesis. That could be that yes, IT profile, the hypothesis could be prolonged sitting causes increased incidence of lower back pain among IT professionals, something like that. So next, I'll tell you what the uses of descriptive epidemiology are. So your descriptive epidemiology will help you just identify that what is the burden of the disease within that particular group or a community or your study population, that how prevalent it is, then what are the changes in the population due to this particular condition, and so on. So it will also give you clues on what could be the cause behind the disease, like how I just previously, I'll make use of the previous example again, is that, okay, a lower back pain and IT professionals, maybe a prolonged sitting, not enough physical activity, so on and so forth. And so from your this descriptive studies, you will get your the next step would be to move on to an analytical study where you'll try to look for an association between the 2 factors which have been described. So next we move on to analytical epidemiology. So the main difference is that in descriptive epidemiology, we were looking at the whole group, a whole population, and then studying a particular factor within that population. Now, in an analytical study design, our interest would be a particular individual within that population or a particular individual group. And once our descriptive study, it will help us generate what the question or the hypothesis is. And our analytical epidemiology will enable us to test that. So what is done is that here is something which we use, which we call the hourglass analogy. Now, it may not be completely relevant here, but just to make things easier to explain, that we start at a wide, like how an hourglass is. It's wide at the top, it's constricted in the middle, and again wide at the bottom. So when we start, we are at the top of the hourglass, we have a problem and we have our population. So next we narrow it down and to look for specific individuals within the population and look at specific problems. And once we get that, then again, it goes back, it becomes wide again, where we generalize our findings to the entire population whom we had initially considered. So the broad classification of analytical epidemiology are cross-sectional studies, case control studies, and cohort studies. So our okay, just before we get your cross-sectional studies, they are just studies which where we collect data at a particular point of time. Now, while going through previous questions, I had noticed that there was a question, MCQ, which was asked that in a particular place that there was an outbreak of the disease. Okay, now to find out that what caused that outbreak of the disease, which is the study design that you will select. And the options given were your retrospective study, prospective study, cross-sectional study, and case control study. Now over here, the answer would be your cross-sectional study, because you are just looking at a particular point of time, like at that point of time, there was an outbreak of disease in that particular area, and what were the factors at play over there? Like if there was, say for example, if there is an outbreak of cholera, so your cross-sectional study will tell you, you can find out, okay, what was the condition at that particular time of the outbreak, what was the condition of the sewage, of other sanitary facilities, and so on. So we next come to our case control studies. Now, this is again something which you have to keep in mind. Sometimes like a question is asked like, what is the synonym of this study or so and so, like a case control study or a cohort study is also known as, and you'll be given your options. So the synonyms are your retrospective studies, your TROHawk studies, and your case reference studies. Now, these are all the same thing. Now, something which you can remember is that TROHawk, this word TROHawk is actually opposite of cohort. Like if you go from the back to the front, this word spells as cohort. So now some features of the case control studies, which is why it is called a retrospective study, is that both your the outcome and the event, they have already occurred. So you're moving from effect to cause. Your effect is already there, and from there you are looking at what was the cause. And here is where there are generally in case control studies, there are two groups. You have one group who have the disease or the condition and one group who doesn't. Now, again, the most classical example used in case of case control studies is smoking and lung cancer. That so the cases will be your individuals who have lung cancer, and your controls will be individuals who don't have lung cancer. So briefly, just see, this is how the outline of a case control study is. So again, using the previous example, say these are the individuals who have lung cancer, and these are the individuals who don't have lung cancer. And so since we are seeing smoking and lung cancer, so we go back and see that how many of the individuals who had lung cancer, they were smokers, how many were not, and the same thing in the control group as well. Now, from the examination point of view, more questions are asked on, instead of the details of case control studies, is their analysis and interpretation. Sometimes what I've noticed in questions is that they'll give you a table like this with numbers, and they'll ask you, they'll give you four options, that what is the odds ratio of this? Or if they give you a cohort study, that what is the relative risk? So I'll just brush you up on that so that it'll be easy to understand. Now, so then always case control studies, you have your 2x2 table. So the A stands for the cases who were exposed. So basically your A is smokers who have lung cancer. Now your controls are non-smokers who have, your smokers who don't have lung cancer. Now among the non-exposed, these are your non-smokers. So your C is non-smokers who have lung cancer, and your D is non-smokers who don't have lung cancer. So how this is interpreted is that, say here the numbers are given. So your total number of cases is 35, and your total number of controls is 82. And from there you have 88 smokers and 29 non-smokers. So just remember these, like A plus C, B plus D, A plus B, and C plus D. So the two things which we do in the analysis of this is, first we'll see what was the incident, exposure rates, incidences in cohort studies. So how many of the patients suffering from lung cancer were smokers and how many were not. So here you'll get your exposure rate is A. So A is your smokers who have lung cancer, and your A plus C is your all total lung cancer cases. So this is A divided by A plus C. So this will give you your exposure rate among the cases, which is patients who have lung cancer. So 94% of lung cancer cases were exposed to smoking. Now next, when we move on to your controls, so that is B plus D. So this is your thing that the non-smokers, smokers who don't have lung cancer divided by the B plus D, which is your total of those who have like host smokers and non-smokers. So from your controls, you can say that the exposure rate among the controls, that 67% of the controls are smokers. Now, the next part is where you obtain your odds ratio. So this is also known as your cross product ratio. So here is that it's a measure between your risk factor and your outcome. So your A is smokers who have lung cancer, B is smokers who don't have lung cancer, your non-smokers who have lung cancer, and your non-smokers who don't have lung cancer. So it comes up to, like, if they give you a table, you remember, so A, B, C, D, it'll be like that. So A multiplied by D divided by B multiplied by C. So this gives us, like, if we, from the previous example, this will give us a number of 8.1. So how we interpret this number is that smokers have 8.1 more odds of getting lung cancer than non-smokers. So another, this is just again for your reference, because sometimes they do ask, like, they'll give you a name of a study and they'll either ask you to identify that what was this study, like whether it was a case control or a cohort study or an experimental study, or even sometimes they'll give you the name of the study, like in these particular examples, although it's self-explanatory, but also that what did this particular study explore. Like for example, there was one question where it was asked that where the name was given, that what was the wipe home study used for. Now the wipe home study is it's a randomized controlled trial, and that was mainly to look at the effect of sugar and dental caries. So the answer for that question would be like dental caries. Now, so this particular one, this is oral contraceptives and thromboembolic disease. So again, this is, if you see this name, you'll know that this is a case control study. And even if you see thalidomide tragedy, because these are like the most like famous, like the other classic case control studies, so their name might pop up. So next, moving on to our cohort studies. So again, like the previous one also, it's important to just remember the synonyms of cohort studies also. Now, the main difference is that case control study is your retrospective study where you're looking back, and your cohort study is your prospective study where you're looking forward. So hence the names incidence study, forward-looking study, longitudinal study, prospective study. Now, from our cohort studies, we get our incidence rates, hence also the name, that why it's also called an incidence study. And so forward-looking prospective, that's pretty much means the same. Now, longitudinal, what it is again, like longitudinal and cross-sectional are opposites. So if you come across the word longitudinal, automatically you should associate it with a cohort study, is because you are observing at different points of time. Your observation A is at the beginning or the baseline, and then as time passes by, you're making more observations, making it a longitudinal study. So the basic design is that here again, so the main difference is that like your case control study is going from is going from cause to effect. Your cohort study is going from your, sorry, I messed it up. The case control study goes from effect to cause, whereas your cohort study goes from cause to effect. Like we have the cause or the exposure. Now again, if I take the same example of smoking and lung cancer. So when it comes to a cohort study, then we will just know that the risk factor is smoking. Now, among the smokers down the line, how many of them develop lung cancer and how many don't? So at the beginning, our entire population is without the disease. From there, we'll identify our smokers and non-smokers. And at the follow-up, we'll observe that how many of them developed the disease and didn't in both the groups. Now, types of cohort studies. Here, if you like see the word a retrospective cohort study, don't be confused. Like if only retrospective study is mentioned, you can be rest assured that they are referring to a case control study. But if you see retrospective cohort study, then that is different from a case control study, because what we do is that although both the exposure and the outcome have already occurred, we do not go from the outcome to the exposure. We will go back to where the exposure started and then follow it till the outcome, although both have already occurred. So that is the basic difference between a case control study and a retrospective cohort study. Now, the prospective one is what I explained previously, and an amphispective one is where it combines both of these. So it starts with a retrospective cohort study, which comes to the present time, and the follow-up continues. So again, next coming to the analysis and interpretation in cohort studies. Now again, you might be given a table like this, and they might ask you to calculate from that, give you options and ask you to identify that which is the incidence rate, or what is the relative risk, or even the attributable risk. So these are the three findings what we obtain from a cohort study. Now it is same like a case control study. You'll have your 2x2 table. So again, here you have like your exposure, and here you have your outcome. So here you have your smokers who developed lung cancer, smokers who didn't, non-smokers who developed lung cancer, and non-smokers who didn't. So again, we have our A, B, C, D. Just remember the position A, B, C, D, and then if you just remember like which is which, like for example, in a case control study, it was A, D by B, C. So if you just remember these letterings, it'll automatically be easier for you to pinpoint your answer, that which is the correct one. So here we've got our A plus B and C plus D. Now, so your incidence rate will tell you this is nothing but this is A by B, and this is your C by D. That what is the incidence of lung cancer among smokers and non-smokers. So from here we'll get like, and always remember one thing, whenever whenever we speak of incidence rates, it is always in per thousand. It's never your percentage. So here we have 10 per thousand in case of smokers, and 1 per thousand in case of non-smokers. So next, coming to how we'll get our relative risk. So we've already got our incidence rates. So from that, we'll get like your relative risk will be the incidence of the disease among the exposed divided by the incidence among the non-exposed. So if I go back to this number again, so your relative risk will be 10 divided by 1. Okay. And the interpretation is, no, sorry, the interpretation of your relative risk is that what is like how much are the exposed individuals more at risk of getting the disease. So when we get a value of 10 in this example, so we conclude that smokers have a 10 times greater risk of developing lung cancer compared to non-smokers. Now, you might ask like, what's the difference then between an odds ratio and a relative risk? Now, in an odds ratio, the main thing what we have to observe is that both the both the outcome and the exposure, they have already occurred. and we'll go back and see that how many of them were actually exposed. Whereas in case of your relative risk, it is, we'll say that it's more like prospective, that these who were exposed, they have a greater chance of getting the disease. And finally, it comes your attributable risk. So what your attributable risk will give you, like how you calculate that. So your incidence rate among your exposed minus your incidence rate among the unexposed divided by the incidence rate among the exposed. So going from the previous example again, so it'll be 10 minus 1 divided by 10. So when we get a percent of that, we'll get 90%. Now how we again interpret the attributable risk is, we'll say that among lung cancer cases, 90% of them were smokers. Or in other words, it can be said that 90% of lung cancer cases are due to smoking. Okay. So again, coming like back to like the milestone studies. So remember this name, Doll and Hill, because this is also like in this subject, a favorite, like this name's a favorite of this particular study. So if you see in any question, if just Doll and Hill study is mentioned, that just please remember that it's a cohort study and it is to do with smoking and lung cancer. And also if you just see, they might not, if they ask a question on this, they might remove the word heart. So if they just give the Framingham study, or even another thing is if a question is asked like, which was the longest running prospective study? So again, the answer to that would be this one, the Framingham study, which looked at like various factors in association with cardiovascular diseases. So next we move on to the final one, which is our experimental epidemiology. So mainly remember these keywords, that your experimental epidemiology will help us measure the effectiveness and the efficiency of the services in prevention, control, and treatment. Now, again, in case these words do pop up in questions, like just I'll tell you how you can differentiate between these two terms, effectiveness and efficiency. So your effectiveness is whether you're getting your desired outcome or not. That whether, say, if we are trying to achieve, say, if I take a vaccine, for example, that whether we are achieving the immunity or not from the vaccine will tell us the effectiveness of the vaccine. And when we come to efficiency, so that is what is the quantity of the vaccine which is required to achieve the desired immunity. So the lesser quantity that is required, the more efficient it will be. So that's your difference between effectiveness and efficiency. So again, like with the previous examples, James, if you see this name, James Lind, or like it might be the British sailor study, or something like that. If you see it, you know that that is your randomized control trial. And in fact, this is the first documented randomized control trial performed by James Lind on British Navy sailors. So just briefly telling you like what, like the thing was that it was to check like how vitamin C can help in scurvy. So he divided like the 12 sailors into groups of 2, and this is what he had given to each of them. And so what he observed was that the group who received the lemon juice or the orange juice, they were cured of the scurvy. So again, remember James, if you see James Lind's name, or the scurvy experiment, or anything, any of this, it might also come. So the basic, like how the design of a randomized controlled trial is, you'll have your population from whom you'll select your samples, and then here the keyword is randomized. So randomization is done. So that could be like simple, like through a lottery method or a chit method or so on. and then we give our intervention. So one group receives the intervention and one group receives like either, now here it's like where vitamin C is given and vitamin C is not given, that's a placebo. Now also we used our randomized trials to test a new drug or a new agent against a gold standard. Like for example, if I take mouthwashes or mouth rinses, so whenever a new product is formulated, it is always tested against chlorhexidine, which is considered to be the gold standard. So that could also be like the non-intervention group, who either they don't receive anything or a gold standard or a placebo and so on. And then finally, we'll check for the effectiveness and the efficiency in both the groups, like whether we are getting our desired results or not. Now, a couple of the randomized controlled study design. So we have our parallel designs and crossover designs. So as the name suggests, in a parallel design, we'll have just like two groups, that one gets the intervention, one doesn't get the intervention, and we just check for the outcome. Now, what we do in a crossover design is, say the first group A and group B. So in the first phase of the study, group A gets the intervention where group B is your control. So then a particular period, which is known as the washout period, this entire portion, this is the washout period, that is allowed. It could be anywhere between a few weeks to months, and then the groups are interchanged. So group B will receive the intervention and group A will be used as the control. So that kind of brings us to the end of the basics of epidemiology. So if there's any part which you want like us to discuss more about, or anywhere where there's a doubt or anything you'd like to discuss, so please make a note of that. We'll be going over those at the end of the session. Now, part 2 focuses on mainly our biostatistics. So here we'll be mainly discussing about data, what is your data, how is data classified, the presentation of data, and then finally we'll be moving on to the statistical tests, where pertaining to these particular exams, that what sort of questions are asked. So moving on with biostatistics. Now, just for an introduction, that statistics is a science of collection, organization, presentation, analysis, and interpretation of numerical data. So in our health sciences, we have our health statistics, we have medical statistics, and we have vital statistics. Now, if you see these names, like if they give you like one of these names and ask you that what all falls under it, like sometimes the question on vital statistics is asked that what where they have spoken about like the age, the sex, then if there's anything on birth rates, death rates, and so on. Then that is your vital statistics. So statistics, they can broadly be classified as your descriptive statistics and your inferential statistics. Now, your descriptive statistics is basically like this is where your measures of central tendency, your measures of dispersion, and so on and so forth will come, like your mean, median, mode, then your range, your deviation, standard deviation, and so on. And your inferential statistics, so this will include like your tests of significance. So important ones pertaining to these competitive exams are your t-test and the variations of that. Then your ANOVA, your chi-square test. Mostly this, like it's very rare that questions on correlation and regression are asked. So we'll be focusing on the other ones first. So moving on, like the basic, like what are the types of data? So your data based on the source, it can either be classified as your primary data or your secondary data. Now the primary data is the one which we collect, say, for example, if we conduct a study or we conduct a survey and we directly collect information from the population. So that is our primary data. And our secondary data is the one which we obtain, which is already collected beforehand, and we use that data. Say for an example of this is our databases. Suppose now if we take data from WHO, or if we take data from the government, so that will be our secondary data. So now coming to the types of data, we have our numerical data, which is our quantitative data, and our qualitative data. So under quantitative, we have our discrete and continuous. So discrete are the whole numbers, and the continuous are numbers which can have decimals or which can be in fractions. And your qualitative data is mainly where it's like that is your coded data. So the alternative one, like what dichotomous means is that there are two options, that yes, no, good, bad. These are your dichotomous data. And the non-alternative ones is where we give a score. Say for example, on a scale, we score 0 to be poor, then 1 to be average, 2 to be good, 3 to be very good, and so on. So that will fall under your non-alternative. And next, when it comes to that, for which data, what scale we use. So when it comes to our qualitative data, we'll be using our nominal scale and our ordinal scale. Okay. And whenever it comes to numerical data, like either we get whole numbers or we get our fractions and decimals. So that is where we'll use our interval scale and ratio scale. So remember, for qualitative, it's nominal and ordinal, and for quantitative, it is interval and ratio. Now, next, we'll be coming to the presentation of data. Now here, what it is important to remember, what we need to know is that sometimes they'll give you a picture like this. Okay, and they'll be like, identify what diagram this is, or what is the data which is given. So first we have our bar diagrams. So again, bar diagrams, again, the sub question might be asked that what type of a bar diagram is this? So a simple bar diagram will just have single bars. Now the compound ones is where we'll have like, say for example, the simple one just has one, like we are just seeing one particular variable. In our compound one, we'll have, and the proportional ones, we'll have multiple variables. So when you see side by side, say this blue line, it is for like, as it's given over here, that subject wise, or if we have like male, female, and combined, and so on. So when they are side by side, it is a compound diagram. And when they are one on top of another, so that is when it is your proportional bar diagram. Now a pie chart is where that will be a circular diagram, which will be a full and parts of that will be segregated. That's how you can identify that. And if in any diagram just a picture is given, so that will be your pictogram. So also next, moving on to our quantitative data, again how the diagrams are. So whenever you see like there is quantitative data, generally we like say for bar diagrams and all for qualitative data. Now for quantitative data, when you see the bars like aligned one beside the other without any spaces, so that is when it is referred to as a histogram. And if you see a histogram which has a line on top of it, that is called a frequency polygon. So remember the difference between the two. And here we have our two more, the frequency curve and the line graph. So both here, now what you need to see is that the difference between the two, like these two look like the same thing, but how can you identify that which is a frequency curve and which is a line graph? So now, as the name suggests, you look out that what is exactly given in the diagram. That your line graph will just tell you that at one point, what the data is. Like here it is comparing your temperature to the days of the week, that at what day, what was the temperature. But your frequency curve is looking at that how the frequency of a particular event is varying. So whenever like a count becomes involved, so then it is your frequency curve, and whenever it's just like you'll get two sets of variables and you compare them with one another at different points, that's your line graph. Now moving on to the descriptive statistics. So this is, we'll have our measures of central tendency, frequency, dispersion, and position. So measures of central tendency, sometimes like, again, for example, like a question was asked that which of the following is not a measure of central tendency. So the options were mean, median, mode, and range. So naturally, since the range is the one which is not among these three, so that would be the answer. So similarly here, you don't really need to know the details of all of this, but just remember the names. So in case a question is asked, it will be easier for you to identify. So means, we have weighted means, harmonic means, and geometric means. We have our median, and in mode we have the unimodal distribution and bimodal distribution. So main thing is just keep these names in mind. So harmonic mean, weighted mean, geometric mean, all of these. Your median is the mid value. This is not all that important. Mode is whichever is the one which is observed the most. Next, again, moving on to the measures of variation or dispersion. So here again, the ones to remember is, remember the term range. So also if you see interquartile range. Next is our deviation. So remember, like it can be the mean deviation, standard deviation, and so on, and variance. So even like if a question is asked that which of the following is a measure of variation or is not a measure of variation, so you'll know what the answer to that is supposed to be. Now, same when we come to our measures of frequency. So our count, proportion, ratio, rate, and risk. So all of these are our measures of frequency. So again, just it's important to remember these names. And finally, we'll come to our measures of position. So here we'll have our percentiles, again, deciles, quartiles, it's all thing like they're all just different breakups of the same thing. We have our hinges, summaries, plots, and outliers. So again, main thing is just remember these names. Next, moving on to the normal curve. Now, again, sometimes like the question is asked on this, like they might just give you this diagram and ask you to identify what it is, or even like here, you remember the word bell-shaped. Okay, so a normal curve is supposed to be bell-shaped. So it is also known as a bell-shaped curve. And also the most important thing to remember about this is that in a normal curve, the mean, the median, and the mode are all the same. So you might be asked a question like this also, that in which of the following curves is these three the same, like mean, median, mode equal, or anything like that. And also, so what your standard, what your normal curve will give you is that, so at the center you have your mean, median, and mode. And so the entire curve, like it actually, the normal curve extends from minus infinity to plus infinity, but there are 3 points of interest to us on either side. That is your mean plus minus 1 standard deviation, 2 standard deviations, and 3 standard deviations. So again, remember these numbers as well. Like they might give you one of these numbers and say that which of the following represent, they'll give you these as the options, and which of the following, like this percentage is representative of which of the following. So your mean plus minus 1 standard deviation is 68%. That means 68% of your population is within 1 standard deviation from the mean. 95% of your population is within 2 standard deviations, and 99.7% of your population is in between 3 standard deviations. Now the remaining 0.3%, those are what you call your outliers, because they do not fall as this curve goes from a minus infinity to plus infinity. So your 0.3% is outside the curve. So again, now coming to variations of the normal distribution. So here we have two, again, skewness and kurtosis. Now again, this is just remember these pictures as well, that they might give you one of these and ask that which, that is this positively skewed or negatively skewed, or when it also comes to kurtosis, is it like positively kurtosed or negatively kurtosed? Like in fact that they can give you a diagram like this, and those can be your 4 options: positive skewness, negative skewness, positively kurtosed, and negatively kurtosed. So what happens in our positive skewness is that the mean shifts to the right, okay? And in negatively skewed, the mean shifts to the left. So when the peak of your curve, like just remember this as the opposite, when the peak, like if you draw a line from the center and this is your plus and this is your minus. So when your peak is in the minus side, that is when it's actually positively skewed. And when it is on your positive side, it is your negatively skewed. Now in another way how a question might be asked pertaining to this is if they give you a statement like, say, so this is like increasing number, right? So if they ask you that if your mode is greater than your mean, what type of skewness or kurtosis is it? So kurtosis is not relevant here, but that might be one of the options. So when the mode and the median, they are greater than the mean, that is positive skewness. And when the mean is greater, so that is your negative skewness. So remember that as well. So next we move on to kurtosis. So when your curve is a normal bell-shaped curve, so there is no kurtosis in that. Now one thing you have to remember in kurtosis, even like if there is positive or negative kurtosis, the mean, median, and mode remain the same. There is no, unlike skewness where the mean, median, and mode vary, there is no difference in the mean, median, and mode in kurtosis. So you have your positive kurtosis when there is a very sharp rise. The mean, median, and mode are still the same, but whereas this would have been your bell, this is how it looks. So whenever you see a peak or a mountaintop, so you know that is positive kurtosis. And conversely, when you see a flat, this is also like might be referred to as the plateau curve. So when it is flat, that is its negative kurtosis. So high peak, positive, flat plateau, negative. So similarly, also you might be given one of these diagrams and be asked to identify that what type of kurtosis it is. So next we come on to our hypothesis testing, which is where we will get into the details of our inferential statistics. That often questions are asked, like you'll be given like certain, you'll be given a statement that such and such a study is being conducted, and so what type of study will be used. So for example, a question might be asked like, say that you have 30 participants, one in group A and one in group B. So say group A is receiving treatment A, group B is receiving treatment B. So you want to find out if there's a difference between the treatments. What test will you use? So that I'll be explaining right now. So the main thing what we get from these tests is that we'll find, like, these tests will tell us that if there is actually a statistical difference or not between two factors, that whether it's happening by chance or whether it is the result of, could be different interventions, different treatments, like any difference which we are observing. So before that, again, this is something, again, please remember this, questions are asked, like you might be asked that what is, like say if you accept or reject your null hypothesis and the opposite turns out to be true, what type of an error it is, or what is, like if they ask that power is of what, then your confidence interval is of relating to which type of error. So first, like I'll just tell you what like a null hypothesis and an alternate hypothesis is. So your hypothesis is your question. Okay, so it's basically your research question. Now I'll take a very simple example. Say I've got two dental materials with me. I've got GIC and silver amalgam. Okay, and I want to compare that. Is there any difference in the retentive capability or whatever in the bond, or say compressive strength of the two materials? So my null hypothesis will be there is no difference in the compressive strength of GIC and silver amalgam. Whereas my alternate hypothesis will be there is a difference between the compressive strength of GIC and silver amalgam. Now, now say I find out that silver amalgam has a better compressive strength than GIC. So that is we are getting a true negative. So that is I am rejecting my null hypothesis that there is a difference, amalgam is stronger, and I am getting a correct result from that. Now opposite will be like where I accept the null hypothesis is I find out there is no difference in the compressive strength between between GIC, the compressive strength of GIC and dental amalgam. So, but however, if there is no difference, okay, and I say that there is a difference, that is my type 1 error or a false positive, that actually there is no difference in the compressive strength of the two, but I am saying there is a difference. So I have committed a type 1 error. So when it is true and you have rejected it, that's your alpha. And when it is false, but you accept it, that there is actually a difference in the compressive strength of GIC and amalgam. But I'm saying that there isn't a difference. I am accepting the null hypothesis that there is no difference in the compressive strength between the two. So there I have committed a type 2 error, which is a false negative. So that is beta. Now, how again this comes into play is that our type 1 error, that will give us our significance level. Okay. So, and also if you see the word like confidence interval is associated with type 1 error. We can say that, okay, 95%, of our observations in the study is not by chance. That 5% can be by chance. Okay. That is your confidence interval or your significance level. And this is from there, like this P, your P number is the probability number. So when you set your significance level at 5%, that comes to a 0.05 P number, which is your probability number. Now, upon conducting a test, like if you, a question like this also might be asked, that they'll give you the P value and they'll tell you that this is wrong. So what type of an error is this? So whenever the P value is less than 0.05, you are safe. Like you think like, it's correct. But if the P value is greater than 0.05, and the null hypothesis is rejected, so there comes your alpha. You've committed a type 1 error. And your beta is the power of the study. So here beta is 20%. So here again, what you can say is that 20% of my observation can be due to chance, right? So just a brief comparison of type 1 and type 2 errors. So type 1 error is where we reject a correct null hypothesis. And your type 2 error is where we accept an incorrect null hypothesis. So your type 1 error is a false positive, while your type 2 is a false negative. Then here I mentioned this point just now. So your type 1 error is a false hit, that you feel you have hit the target, but actually that's not the case. And type 2 error is a miss, where the target is just that we've gone off, haven't hit the target at all. So when it comes to the significance and power, significance or the confidence interval is associated with type 1 error, and the power of your test is associated with type 2 error. And of course, your type 1 for alpha and 2 for beta. So next we'll look at tests of significance. Now, when is like the main classification is we'll have our parametric tests and your non-parametric tests. So here we have our t-test, our z-test, our ANOVA. Now here it's like generally the non-parametric tests, they are non-parametric versions of the parametric tests. Now there are certain assumptions that need to be made. Now one thing is like, again, from the point of view of these competitive exams, again, going back to normal distribution. For all parametric tests, it is assumed that the distribution is normal. So if you get a question where it has been mentioned that whether your data is normally distributed or not. So the moment if you see that word, if you see the thing that the data is normally distributed and you have one of these options, you can go for it. Whereas if it is mentioned that your data is not normally distributed, again, there, if you see any of these names, you go for it. Now, another addition to this will be also the chi-square test, okay? The chi-square test is also a non-parametric test. Another way how you'll know whether to use a parametric or a non-parametric test. Now, if you go back to when I spoke about the data. So whenever we have our quantitative data, that is we have our numerical data, okay, which could either be the discrete or the continuous data. For those, we will use our parametric tests. Whenever we have non-parametric data, okay, for those, we will be using our non-parametric tests, including chi-square tests. Like the most popularly used test of significance for your qualitative data is chi-square. So just keep that in mind. So as I just mentioned before, just now, that parametric tests normal distribution, non-parametric not normal. Also, another point is that if like whenever our samples are randomized, whenever we follow randomization, we'll use parametric tests. Where we do not randomize, we'll use our non-parametric tests. Quantitative data, parametric; qualitative, non-parametric. And again, when it comes to the measurement scales, ratio and interval for your discrete and continuous, parametric. If it's nominal or ordinal, like count data, then we will use the non-parametric tests. So now just briefly, we'll be going over the parametric tests. Again, I won't be getting into the nitty-gritties of each of these tests, but we'll be focusing on more like what is important in relation to the questions which are asked. So students, the t-test, also known as students t-test. Now remember this name again. So the name of the person is William Gossett. So his pen name was student, which is why it's called the students test. So in case they ask like who gave the students t-test, or if you see Gossett's test also, don't get stumped if you see the word Gossett test. It's nothing but your t-test. So basically what our t-test is doing is telling us whether there's a difference in the means or not. Now, again, coming back to the example which I had taken earlier, is that if you get a question that there are 15 participants in each group, one is getting treatment A, one is getting treatment B. So what test will you use to find out the difference? Okay, so over there, your answer will be t-test. You're getting the difference. Now, what you need to remember from t-test and this is that we use the t-test for a smaller sample size. So in questions where the sample size has been mentioned, if the sample size is less than 30, your answer will be t-test. However, if there is like the same question is asked that there are so and so many people in two groups, treatment A, B, if the number is above 30, say if they give you a number of 40 or 50 or 100 or whatever, that is when we will be using the Z test. All right, so less than 30, t-test, more than 30, Z test. Both the tests are doing the same thing, that is finding a significant difference between the means, okay? Also, another important point to remember is whenever like these tests are like, it could be the t-test or the Z test, or even ANOVA for that matter, I'll be talking about that in just a moment, that they will just tell you whether if there is a significant difference or not. They cannot tell you how significant it is. Like for example, they can't say that say treatment A is 10 times different, or we can't say better or worse also. They'll just say that treatment A and treatment B have a difference. That's all. So again, like I mentioned, so again, criteria, just watch out in the questions which involve statistical analysis where you're given a problem and you have to select. So just see if they've used the words. If they use the word random, you'll know again, you can use parametric tests. So your t-test, z-test, ANOVA, all of them apply. Again, data must be quantitative and less than 30 and normally distributed. So just keep these key points in mind. So again, your t-test will have classifications. So you'll have your single sample t-test, independent samples t-test, and paired t-test. Now, again, coming to like the problem type questions, just keep a lookout. So now in your single sample t-test, you will have just two separate groups, okay? Now in your, you'll have just one group. In your independent or unpaired t-test, you'll have two different groups. Like say if, again, like the same example, which I said, that there's group A and group B receiving two different types of treatment. So there, if you see something like that, over there, we'll use our unpaired t-test. Now, where we'll use a paired t-test is there's only one group, but we are observing them at different points of time. So again, if say only group, say they give you a question like 30 participants, they were like assessed at the beginning of the treatment and they were assessed at the end of the treatment. So to find out that if the treatment made any difference in them or not, we will use a paired t-test because the sample group is the same. We are just checking them before and after. So if a question like this comes where you see that it's before and after, it's a paired t-test. If there are two groups, you use the unpaired t-test. And so this is just again, take a look at this formula. As such, the details of this formula are not required. It's not usually such like, you won't get formulas and be asked to identify tests, but just it's there for your reference. So here, like I mentioned just now about the paired t-test. Next, we'll be moving on to the chi-square test. Now, like I mentioned, that it is the, again, simplest and most widely used, the most popular non-parametric test is your chi-square test. Okay. So it will just tell you if there is a difference between the observed frequencies and expected frequencies. Now, what this means is that, say, for example, that I have a number that, okay, the prevalence of dental caries in the population is, say, X, for example, and I conduct my survey and I get a value of Y. So using X and Y, and I run the chi-square test, it will tell me whether that there is a statistically significant difference between X and Y or not. So this is like, in a very simple way, the chi-square test explained. So whenever that you see a question, that again, one is the important is that this is for categorical data. So in questions like to see that is there a difference in that what you are expecting and what you are observing. So over there, we'll have our chi-square test. Also, the chi-square test has three functions. So just remember this. So in case, just remember these three terms. That, and if you see these three terms and you see chi-square test all like in the same place, you'll know that it's all associated. So that's your test of association, your test of proportion, and your goodness of fit. Now, the third point won't change any of the problems, but the first 2 points might. So again, so this is how your chi-square table, now the chi-square table is also similar to our case control and cohort studies tables. It is a 2x2 table. Now here, again, remember A, B, C, and D. So your this is your row total. Okay, so you have R1 and R2 and your column total, C1 and C2. So to get the difference between the observed frequency and the expected frequency, so your expected frequency will be your row total the row total into the column total divided by the grand total, which is N. So N will be A plus B plus C plus D. Again, this is not, again, just the formula is there for your reference. As such, no. So then also if like a question comes where they tell you that the chi-square value was found to be greater than or lesser than the critical value, they might just mention the word critical value. So then you'll know that if the chi-square value is greater than your critical value, that means there is a difference. So you'll reject your null hypothesis. But if the value is less than, your chi-square value is less than the critical value, so then you will accept your null hypothesis that there is no difference. So again, a limitation of the chi-square test is that it just indicates that whether there's an association of not or not, but it won't tell you if there, like, what is the strength of that association. So for that, we'll need to use correlation. And also it does not tell us the direction, that whether it's plus or minus. So in that respect, even our t-test, z-test and all are similar, that they'll just tell us if there's a difference or not. So after the t-test and the z-test, now in both of these, like, either there is a single group or a there is either a single group or multiple groups. Now, when there are more than that, so that is when our multivariate analysis comes into play. So over there, we have our ANOVA. So that can be one-way ANOVA, two-way, the different, like, just again, Mainly one-way and two-way are important in this aspect, but just remember these names. If you see Manova or Ankova or Mankova or all of these, it's just all different variations of ANOVA, which is short for analysis of variance. And then we have our regression analysis. So just again, the names are more than enough. We have our linear regression, complex and logistic regression. And we have our functional analysis, discriminant analysis, structural equation model, and path analysis. Another one is factor analysis. So if you just see these names anywhere, so they are all associated with multivariate tests. Now, beyond the names of the questions, generally, you won't get, like beyond the names, you won't get questions on these topics. So again, ANOVA, it's important to remember the name of the person who gave it. So it was Gossett for student, like t-test. His pen name was student. Then it was Carl Pearson for chi-square test. And it is Fisher, Ronald Fisher for ANOVA. So the types of ANOVA are like your one-way, two-way, and three-way ANOVA. So again, it'll just tell you like the difference between the groups. So in one-way ANOVA, you are checking one variable, like one to your outcome. Okay, so here our outcome is the BMI, which is the body mass index. And we want to see that what are the factors that affect the BMI. So if we have just one factor, which is the socioeconomic status. So there we have our one-way ANOVA. So if we've got socioeconomic status and age, that's two-way ANOVA. We have two variables looking at the outcome. And we have three-way ANOVA. So that is your effect of age, SES, diet on BMI. Now, another way how these like particular variables might be titled as, so you see the word on here. So it means SES on BMI, right? So your SES is your independent variable and your BMI is your dependent variable. BMI is dependent on SES, right? Same. So here we have two independent variables and one dependent variable. BMI is dependent on SES and age. Same for this one. Okay. So that kind of brings us to an end on the statistical portion of it. So we will end today's session over here. So now if there's any, like, if anyone wants to ask something or discuss something, or if they want like from this particular, these two topics of your epidemiology and applications and biostatistics, if they want something to be discussed, then we can go ahead with that. And also if anything you'd want, like again, a presentation of any particular topic tomorrow, we can do that as well. So where is, I saw someone raise their hand, like if you could unmute and wait, where is the chat? Okay, so Mansi has a question on the Z score. Okay, so now your Z score is, again, like once you from like the t-test, there is a formula for the Z test. Now the thing is, again, you have to compare your Z score with the table value. Now there are statistical tables for each of these tests. Like you have a T table, you have a Z table, you have a chi-square table. So depending on what like your parameters of the test are, you will look for the critical value. So if your score, like if the Z score is greater than the critical value, which corresponds to the one on the table, like as per your test, if it is greater than that, so you will reject your null hypothesis. That means there is a difference. Like again, going back to GIC and amalgam. So if your Z score is greater than the critical value, you will say that yes, there is a difference between GIC and amalgam. If your Z score is less than the critical value, you will say that there is no difference. Okay, so now we have a question from Payal, null hypothesis. Okay, so what does the word null imply? Null implies nothing, right? So your null hypothesis is one where there is no difference in the groups. Okay, so my null hypothesis would be there is no difference in the compressive strength of amalgam and GIC. Or also, like, my null hypothesis will be that there is no effect of sugar on dental caries. Whereas then from my null hypothesis, I will get my alternate hypothesis that there is a difference between the compressive strength of GIC and amalgam, that there is a difference, like sugar does cause a difference in dental caries. Okay. Is null hypothesis clear? Okay, so Mansi is again asking that in which cases will we use a cross-sectional study? Now, a cross-sectional study is also called a point study or a prevalence study. Okay, so whenever if you see any question or later, whenever that they ask you, where they ask you about that what is the particular cause at that point. Like I mentioned that I saw a question that they'll tell you, like, suppose there is a cholera outbreak in a neighborhood. Okay, so what type of study will you use to determine what is the cause of that outbreak? So over there, we'll use our cross-sectional study, that at the point of the outbreak, what were the conditions? Okay. So your point study or your prevalence study is cross-sectional. Also, if a question is asked that what study design will you use to find out the prevalence of dental caries in school children at a particular point of time? Over there, you will again use your cross-sectional study. Okay. Okay. Shayon is asking that, can you please repeat retrospective cohort study and negative skewness? Sure. Okay. So see, the point which you have to remember is that in your cohort study, you are going from your cause to effect, from your exposure to your outcome, right? Whereas in a case control study, you are going from your outcome to your exposure, like from the effect to the cause. Now in a retrospective cohort study, although the outcome has already occurred, but we start following it from where the exposure started. We don't go back. Like say, again, if we are in a lung cancer and smoking case control study, we will see that, you know, that this person has lung cancer. So for how long has he been smoking? So we'll go back and see. But whereas if we are doing a retrospective cohort study, we will directly start at the point where he started smoking. Okay, so say that's 10 years back. So we will start our observations from 10 years back and come back to the present day. Okay, so that is your retrospective cohort study. Now, for a negative skewness. Okay, so the bell-shaped, wait, can I? No, how do I open? I'll try to draw the negative skewness. So the thing is that this will be like roughly a normal curve. Like just assume this is the normal curve. Okay. So in negative skewness, what happens is that there is a shift of the peak to the right-hand side. Okay. So this is your mode. Your median is here and your mean is here. Okay. So your mean, like your mode is the greatest and your mean is the smallest. Okay. So when mean is less than median, less than mode, that is negative skewness. Your thing is shifted, like the peak is shifted to the right. Conversely, when the peak is shifted to the left, that is when it will be positively skewed. Like this is your mean, this is your median, this is your mode. So mean is greater than median, greater than mode. Okay. So this is your negative skewness. I hope skewness is clear. Okay, so next is Mansi. Oh no, before that we have a question from Pal again, that how will we get our alternate hypothesis? See, you formulate your alternate hypothesis from the null hypothesis. Like your alternate hypothesis is there is a difference. My null hypothesis will say there is no difference. My alternate hypothesis will say there is a difference. So that depends on what you're studying, or like what your variables of interest are. Like you might be comparing dental materials, you might be comparing two drugs also. Like say if I compare, or simply put, say I'm comparing Colgate and Pepsodent. My null hypothesis is there is no difference in Colgate and Pepsodent. My alternate hypothesis is there is a difference between Colgate and Pepsodent. Okay. Okay, Amansi, why can't we use a case control study? Is this in respect to why can't we use a cross-sectional study? Right?
Yes, sir. I want to ask you why we can't use case control study in the example you have given about cholera outbreak.
Okay. So now, see, the thing is that we are using the cross-sectional study because we want to find out what caused the cholera outbreak. Okay, so over there we are just looking at that particular point. In a we can't use a case control study is because like we would use a case control study if you were asked to study the cholera outbreak, like, and also the I'm sorry, one sec, I just let me regroup. So why it is